If you recall, we've been finding area under a curve. We've been modeling continuous change with discrete change by holding things constant on little bits. We've been turning our continuously changing function into a function that is constant on little bits. And where we landed was here at the first part of the fundamental theorem of calculus. That says if we want to calculate a definite integral, if we want to calculate this continuous sum, we can evaluate the antiderivative or evaluate an antiderivative at the endpoints of our interval. So the definite integral from a to b of f of x to x is capital F at b minus capital F at a, where capital F is an antiderivative of f. That is, capital F prime is f. What's going on here is that we are using an antiderivative to calculate a definite integral. That's what happens here. We're using an antiderivative to calculate a definite integral. The goal is to calculate a definite integral. We are using the antiderivative to do that. So here we are using an antiderivative to calculate a definite integral. We are calculating a definite integral using an antiderivative. One thing that we want to note here, we'll note that in a minute. This is one part of the fundamental theorem of calculus. We can calculate a definite integral using an antiderivative. There is another part to the fundamental theorem of calculus that we need because not all functions have nice antiderivatives. So one thing to note is that not all functions have nice antiderivatives. I haven't defined what I mean by nice, but it's easier than saying finite combinations of elementary functions. So not all functions have nice antiderivatives. So there's a restriction, not a restriction, but a limitation right here. Not all functions have what we'll call nice antiderivatives. Not all functions have nice antiderivatives. That is, not all functions are the derivative of some finite combination of elementary functions. We can unpack that later, but that's what we mean when I say nice antiderivatives. Two parts of that niceness. A nice function would be a finite combination of elementary functions. All the functions that you've encountered up until this point in your mathematical career have been elementary functions. Unless I talked about sine x over x with it. I don't think I have. So we're good. We're good. We're good. Specifically the antiderivative of sine x over x. I don't think it's come up yet. So I think we're good. All the functions you've encountered up to this point in your mathematical career have been elementary functions. Your algebraic functions, polynomials, radicals, rational, your trig functions, your inverse trig functions, your exponential functions, your logarithmic functions, elementary functions. So when we say we can calculate a definite integral using an antiderivative, there's a problem there. What if the function doesn't have an antiderivative? So there's a second part to the fundamental theorem of calculus. It just takes this part and reverses it. So the second part of the fundamental theorem of calculus, we are constructing a function using the definite integral. We are constructing a function using the definite integral. Capital F of x, we're going to define, this is separate from the previous capital F. This is just a new capital F of x that we are inventing right now. And I'm defining capital F of x to be the integral from c to x of f of t dt. I am using the definite integral to define a function. And the fundamental theorem of calculus says a function defined this way will be an antiderivative of f of x. That is, this function prime is f of x. What we're doing in this part of the fundamental theorem of calculus is that we are constructing an antiderivative using the definite integral. So in this part of the fundamental theorem of calculus, we are constructing an antiderivative using a definite integral. We are constructing an antiderivative using a definite integral. It's good that we can do this because not all functions have nice antiderivatives. So if we need an antiderivative of a function for whatever reason, if we can't find one, we can build one. That is a useful thing. We're using the definite integral to construct an antiderivative. The reason that this always works is that for continuous functions, we can always approximate a definite integral with area. Definite integrals we know we can use to find area. So the reason that this is powerful is that we can approximate a definite integral with area to any degree of accuracy up to the limits of our computing power. So the reason that this is good, the reason that this is powerful, this is awesome because we can approximate definite integrals using area. And we can do this to any degree of accuracy up to the limits of our computing power. Because we can improve our approximation by just making more rectangles. These are the two parts of the fundamental theorem of calculus. First, we can calculate definite integrals using an antiderivative. And second, we can construct an antiderivative using a definite integral. The reason the first part is important is that not all functions have nice antiderivatives. That is a finite combination of elementary functions. The reason the second part is interesting is that we can always approximate a definite integral with area to any degree of accuracy that we happen to need. Any questions? So now every function has an antiderivative. It just might not be a nice antiderivative. This is too much to be unloading on you on like the second day of the fundamental theorem of calculus. But I brought it up. It's my fault. I brought up the fundamental theorem of calculus yesterday. I should tell you what the fundamental theorem of calculus is. Too often we just grab onto little parts of things and think we know stuff. Do you know what I mean? Has anybody ever heard the phrase, the customer is always right? Some of you work in retail, and you're like, I fucking hate when they pull that one out. There's more to that quote. Because someone actually did say the customer is always right, but that's not the end of the quote. Customers use it because they think it's like their silver bullet to make you do what they want. What's the rest of that quote? The customer is always right in matters of taste. The customer is right if they taste your soup and they're like, oh, I don't like this soup. That's just true. They tasted the soup. They say, this is displeasing to me. They are correct. But when they're like, oh, you have to give me your money back, my money back, because I don't like this soup, and the customer is always right, that's not a matter of taste. That's a matter of policy. And my policy when people ask for the money back is to say, fuck you, get out of my restaurant. So yeah, the customer is always right in matters of taste. So if you happen to work in retail, just remember that when customers be assholes and be like, oh, no, the customer is always right. Just be like, oh, this ain't a matter of taste, bitch, get out. You know what I mean? Anyway. So I had to give you the whole fundamental theorem of calculus because it came up yesterday. So sometimes the second part is listed as the first part, and the first part is listed as the second part, which means it doesn't matter which one is which. It's just whatever the author decides to put in front of you first. I picked this one. That's what the book happened to do. So I'm like, oh, I guess I'm doing this one first. So if you see them reversed, that is not a gotcha moment. You're like, ah, Leach had these backwards. They can't be backwards. It's not a rule. You know what I mean? How's that right? Okay. Our job is to just, right now, find some antiderivatives. That's the game that we're playing now. Not because in future, you're going to have to use your mad integration skills to find a bunch of antiderivatives. Like your boss isn't going to walk up to your cubicle and say, yeah, I'm going to need you to go ahead and find these antiderivatives. That would be great. And then take a sip of coffee. That's a reference to Office Space. It's not a good one, but it's a reference to the movie Office Space. And if you haven't seen the movie Office Space, that's your homework this weekend. Find the movie Office Space and watch the movie Office Space. Because some of you is going to be engineers, and you need to see what your future is. Even though this movie is like from the 90s, I think it's from the 90s. I don't know when the fuck it came from. It was a long time ago. It is still a glimpse into your future. Working in. So this is the fundamental theorem of calculus as we have it now. So this is where the fundamental theorem of calculus is going to sit while we're doing single variable calculus, because it changes once you get into Calc 3. And there are more fundamental theorems of calculus. But this is where we're at right now. This is all we need right now, these two parts. We can calculate a definite integral using an antiderivative. We can construct an antiderivative using a definite integral. That's a better way to remember these two parts than like all this stuff. Because as soon as you start writing down formulas, you think you've got the whole thing. This is not the fundamental theorem of calculus. The fundamental theorem of calculus starts here with the word let and ends here with this period. The first part. And the second part starts at this capital F and ends at this period here. It's the whole thing. It's not just like the equation looking part of it. All right. Our current job is finding antiderivatives. We added some stuff to our finding antiderivatives repertoire. We integral of x to the n. We add one to the exponent, divide by the new exponent. We also added the plus c, because the derivative of any constant is equal to 0. And we're asking the question, x to the n is the derivative of what function? It's the derivative of x to the n plus 1 over n plus 1, plus some constant that we don't know anything about. So we just put a plus c, plus some constant. That's what the plus c is standing for. That's our constant of integration. Now, this only works if n is not -1. We didn't write that and make note of that yet when we first talked about this. So this is only valid for n when it's not -1, because otherwise you got that big 0 sitting in the denominator. And that ain't no good. You can't have 0 in the denominator. But that's okay, because we also know that the derivative of natural log of x is 1 over x. So the integral of 1 over x to x is natural log of absolute value of x plus c. Now, if you forget the absolute values around the x, I won't kick you out of class. What I'll do is flunk you with so many negative points that you're going to be back in algebra. And we don't offer algebra anymore. So you're technically getting kicked. I'm just kidding. I actually just kicked you out of class. I'm just kidding. It's just not that serious. Same thing as you forget to put the plus c. And I thought, well, I'll just put the plus c, because you remember the important part, how to find the antiderivative. I see teachers all the time, they're like, have the antiderivatives quiz, and they're like, oh, don't forget to put the plus c. It's like, well, why are you going to have them put the plus c if you're going to tell them to put the plus c? That's weird. So if we can write terms with powers of x, then we should write terms with powers of x. Yesterday, we talked about square roots and negatives, including this new negative here. If we can write terms, then maybe we should write terms. So here's an example. Oh, see. Not a sponsored post, but I'll have to go back to the first page of my Rocketbook Flip reusable notebook. And, oh, these don't have the name on it. Pilot friction pens. Don't call me Rocketbook. Not because I'll turn down your money, because I don't answer my phone. I wonder if that's the future. Teachers are going to have like sponsorships, like NASCAR drivers. Like you see a NASCAR driver, they got like sponsorships all over the place. Like they got their like fire suit on, and it's like all fucking Mountain Dew and Tide and all that other stuff on there. So our teachers are going to have to like walk in and, well, I think we should just wear our academic robes and put the ads on that. You know what I'm talking about? You know what I mean? Like the graduation robes. When you get like a master's degree, you keep that shit. And when you go to an official function as an academic, you wear that shit again. I still have, okay, I don't have mine anymore, but I still have like the hood that you put on. It's like when you get a master's degree, you have to wear this extra thing. It's not just the gown and the flat hat, the flat mortarboard hat. You also get like this weird cape type of thing. It's called a hood, but it's more like a cape type of thing. And it's really just a big scarf that goes around your neck and you hang it and you hang it so that it chokes you. It's really annoying. Then, and also your sleeves have these weird long things on it. I think it's to make fun of people with master's degree, but that's beside the point. You have these big things here, which if you have an outdoor graduation, you get your master's degree, drinks fit in there. So you just like have these little pockets and they're like 3 feet long and they drag on the ground if you're short, but it's actually a little pocket and you can drop. I don't think it's meant for drinks, but that's what I did with mine. So I'm like walking down there and I wave to my parents. It's like clink, clink, clink. It's like, what's that clinking noise? It's like, oh, I don't know. I didn't bring any beers to graduation. It's like, well, we didn't even say that, Leach. So well, I panicked under interrogation. But then when you get a doctorate, you kind of go back to your bachelor's degree robe. So that it doesn't have the big long pockets and the weirdo sleeves. You still have to have the choking hood, but it's the sleeves go back to like your bachelor style, but they have like these velvet patches on them. It's weird that we still have that stuff because we don't do the ritual stuff anymore, but there it is. Let's say, suppose we want to integrate. We want to find the antiderivative of x minus 3 squared over x. What we have here is an opportunity to just multiply all this out and write terms. If we can write terms, then maybe we should. So I'm just going to multiply out the numerator, x squared minus 6x plus 9. And then I'll just keep using the distributive property and make x squared over x minus 6x over x plus 9 over x. So just some more distributive property. So I'll integrate a term at a time, and x minus just 6 plus 9 over x dx. If we can use algebra, then maybe we should use algebra. Now I'm actually ready to integrate. The integral of x to the 1 power is 1/2 x to the 2 power. The integral of 6x to the 0 power, I'm thinking of this 6 as 6x to the 0 power. We add 1 to the exponent and divide by the new exponent. And the integral of 9 over x is 9 times the natural log of absolute value of x. What? Is everybody okay? Yeah. X to the first. Okay. Just a quick reminder that x by itself is an x to the first power. So we've got our basic tool. We add 1 to the exponent, divide by the new exponent whenever we can, as long as it's not too inconvenient. If this was x minus 3 to the 10th power, we'd want to find something else to do. But x minus 3 squared, let's just multiply that out. Come on. So we've got the basics of this calculation. Take a moment and calculate the integral from the definite integral from 0 to 2 of 4 minus x squared to x, and then draw a picture of what this represents. So let's calculate this and then draw a picture of what this represents. First, the calculation part. We find an antiderivative for x minus a third x cubed, and we evaluate from 0 to 2. This means we plug in the 2. We plug in the 0. And subtract. So 8 minus 8 thirds. This is all 0, so that's easy. So I have 8 minus 8 thirds. So what's that? 16 thirds. That would be the normal way to say that. I don't know why that counts as a normal way to say that. A terrible way to say it. That's what, 5 and a third. What's 8 thirds? 2 and 2 thirds. So this is 8 minus 2 and 2 thirds. 8 minus 2 is 6. 6 minus 2 thirds. That's also 5 and a third. So okay, we're good. This is just the calculation. Let's draw a picture of what we've calculated here. We're going to be finding the area under the graph of 4 minus x squared and above the interval from 0 to 2 on the x-axis. So 4 minus x squared is this parabola facing down or opening down. On the interval from 0 to 2. So that's what we calculated. That area is 5 and a third. Any questions? Let's integrate this from 0 to 3. What happens at 2 that makes integrating this 0 to 3 going to make some weird stuff happen? What happens to this function when x equals 2? Looking at this picture right here. When x equals 2, the function 4 minus x squared drops negative. The amount that we're subtracting is more than 4, so the value of the function goes negative. And no one ever called me on this under and above business that I kept using, under the function and above the x-axis. No one was ever like, dude, functions can be negative. maybe the reason that no one ever said this is that I don't know if you're comfortable with calling your professor dude. That would be weird. But what happens here is that after 2, this function goes negative. Let's see what happens. Let's suppose that I wanted the integral from 0 to 3, 4 minus x squared dx. So the interesting thing, the new thing in this example is that the function goes negative on this interval. The function goes negative on this interval. So let's find out what happens. Now we're evaluating 4x minus a third x cubed from 0 to 3. So I'm going to have 4 times 3 minus a third times 3 cubed minus, well, 0. At least that part doesn't change. Let's see what value we get now. So 4 times 3 is 12. 3 cubed is 27. Divided by 3 is 9. So now our value is 3. Even though we've got a longer interval from 0 to 3 instead of 0 to 2, our definite integral became less. How would you guess we would interpret this smaller amount in terms of area? What would you say is going on here? From the previous example, this area, the amount of area from 0 to 2 is 5 1/3. But the definite integral from 0 to 3 is only 3. So what happened? Right now I'm building anticipation that I'm just going to be writing down the answer. And I just keep making the lines darker. And it was like, oh, dude, just write down the answer. Some of you can't get over the fact that I did not spread out my 1, 2, and 3 evenly. So what's going on here? What gives? How come we got a lower value? What must be happening with that area between 2 and 3? What is the definite integral calling that area? And how much of it is there? So the explanation is very simple. The explanation is very simple, and all I have to do is tell you right now what that explanation is. Or I could just cut to the chase and say, this is what I want you to think about. I want you to figure out what's going on with this area. And here's one thing that might help you think about that area. Find the integral from 2 to 3 of 4 minus x squared to x. All right, so find the definite integral from 2 to 3 of 4 minus x squared to x. And then think about this picture. Remember this red area up here? That's the 5 1/3 that we got from the previous one, assuming I did the calculations correct, which is not a good assumption. And then, but the total amount from 0 to 3, we ended up with a smaller amount. How could more area have a smaller value? How could we add area to it and get a smaller value? Yes. That is exactly what's happening. That area, the definite integral, reads area below the x-axis, below the function, or below the x-axis and above the function. It reads that as negative area. It's counting that against the total. So from 0 to 2, we have all this positive area. It's 5 2/3. From 2 to 3, we're accumulating more area, but the definite integral reads that as negative. Now, why would the definite integral be reading that as negative when this function goes negative? How come our area started decreasing when the function went negative? That goes back to what we were talking about with sign direction. Now that's it for today. That's what I want you thinking about. Think about how this fits in with what we already know about derivatives, so we can put all this stuff together in our minds. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.